We'll get started with the third module in our airfoil aerodynamics. For some of the aerospace engineering students in our class, this may be very familiar. Hopefully this is a refresher for you. For the mechanical engineering students, you may have seen small pieces of it here and there, but for the sake of completeness, I'm going to bore you to death by going over what we mean by panel methods. When you want to compute a lift over an airfoil, there are two ways or three ways you could do it. One is to wind tunnel test it. Of course, that's very expensive, but gives very reliable answers. You could secondly use a computational fluid dynamics solver, such as Navier-Stokes equations. Use a software such as Star CCM or ANSYS Fluent or some other software to compute the lift and drag. Or you could use the potential flow technique that we developed in our previous module 3.2 to solve the flow over an airfoil. So many software, freeware and commercial software such as Xfoil freeware uses this technique. So we are going to show you how does it compute the lift. So that's what we are going to cover today. So this is basically a technique for solving two-dimensional incompressible potential flow, that means irrotational flow, over thick two-dimensional and three-dimensional geometries. We are, of course, primarily concerned about the two-dimensional geometries. So the airfoil is, of course, a curved surface. From leading edge to trailing edge, upper surface as well as the lower surface is highly curved. So what we normally do is we break it into piecewise straight line segments. We call them panels. Some books also call them boundary elements. For this reason, a panel method is sometimes called a boundary element method. On each of these panels, we are going to put a thin boundary layer. As we know, the boundary layer has got a vorticity. We are squishing it, all of it, so that it becomes an infinitesimally thin sheet rather than a thick boundary layer. So it's got a strength of gamma. These are miniature vorticities. So spread over a length delta S, where delta S is a length of a single straight line segment. So gamma times delta S is called a circulation. It will have units of velocity times distance is called a circulation. There is a theorem called Kutta-Joukowsky theorem that says if you don't have any circulation, you cannot have any lift. So vorticity is what produces lift. So our vortex sheet basically mimics what's going on inside the boundary layer over the airfoil. So in a real airfoil, you have a thick boundary layer. Upper surface, as the flow goes over the upper surface, these molecules are moving fast. The molecules near the wall are staying put. So there's a clockwise rotation. Clockwise rotation. Here the opposite happens, counterclockwise rotation. So this thick boundary layer is squashed into a thin sheet, like a shrink wrap, sheet of plastic-like material, vortex sheet over the surface. So there'll be a clockwise rotation on the upper surface, counterclockwise on the lower surface. If you sum them all up, if you get a net circulation 0, then you'll have a 0 lift. If you have a more of a net clockwise circulation, you'll get an upward directed lift. If you don't have a net circulation is counterclockwise, then you'll get a downward directed lift. So just the sign of this vorticity can also determine the sign of the lift. So this is our panels. This is our actual airfoil surface. I have replaced it with the panels. Obviously, this is a crude location. If I had placed it up here, it'll follow the shape. So whenever we use a panel method, it's important to view the panels to make sure they are a true representation of the airfoil surface. If they are not, you should have more points, more pieces of straight line segments to represent any curved pieces that we are not properly capturing it. It's very important to capture the leading edge region because lots going on there. The more the number of panels, the more accurate the solution, because we are representing a continuous curve by an infinite series of broken straight lines. But this costs a lot. So in many computer codes such as Xfoil, you may use about 100 panel. In my example program, you may use just a 33 or 65. Some very small number of panels is what you use. What type of a boundary condition should we use? Now the flow goes over the airfoil, outer and underneath. The flow streamlines have to be tangent to the surface. That means there cannot be any normal velocity to the surface. So we could treat the airfoil itself as a streamline. So there's a streamline comes here, hits the nose, splits into two parts, one over the upper surface, other one over the lower surface, then leaves through the trailing edge. So that value of the stream function, we call it C. So the boundary condition is at all panels, at the center of each panel, which we call control points, psi must be equal to a constant. Of course, we don't know what this constant should be, so that's one of the unknowns. We also do not know what is the vorticity times delta S is in each of the panel. We know the length, but we do not know the strength, gamma naught. So the free stream function is given by u infinity y minus v infinity x. So why? Because if you take an x derivative of d psi dy, you pick up the x component of the free stream velocity. If you take a minus of d psi dy, we get the y component of free stream velocity. Also, if you plug this u equal to u infinity, v equal to v infinity in here, it satisfies continuity equation. If we put u equal to u infinity, which is a constant, v equal to v infinity, which is a constant, it satisfies the governing equation. So this whole thing satisfies the Laplace's equation, del squared psi equal to 0. If you take a second derivative with respect to x, you'll get 0. Second derivative with respect to y, you'll get 0. When you add them together, the Laplace equation is satisfied. Now we have all these vortices on the surface, so we need to come up with a suitable strength or a stream function. So let's say you have a counter-spinning vortex of strength gamma. It produces a velocity pattern that looks circular like this. So the vortex is at the center, it's spinning counterclockwise, it produces a circulation like this. You'll not have any radial velocity, so Vr is 0. So the v theta times 2 pi r, velocity times distance, is velocity is uniform, times distance is what we call the circulation gamma. So v theta is circulation gamma divided by 2 pi r. Now as r goes to 0, you'll get higher and higher spinning particles. So as you approach the center of a vortex, you'll get very high velocity in the v theta direction. So just as we have a Cartesian representations for stream function, in the polar coordinate system, there are definitions for radial component of velocity in this direction, Vr, which is 0, and tangential components of velocity, v theta, in terms of psi. So v theta is minus d psi dr according to those definitions, which is gamma over 2 pi r. So if you now integrate this, you get a minus of gamma over 2 pi times the logarithm of r. So this is the stream function for a single vortex. Of course, we have lots of panels. Each and every panel has got its own vortex, gamma times delta s. So each and everything produces this type of a stream function, where r is the distance between where the vortex is and where you are computing the stream function. This is always from the center of the vortex. So in our case, let's say you have a panel x naught, y naught. It's got a strength of minus, comes from before in the previous slide. We had a minus here, so we just carry it. So this gamma becomes gamma naught times delta s. This is the vortex strength by 2 pi. logarithm of where the panel is located is x naught y naught, where we are computing the stream function, which is x and y. So the distance between the two is r minus r naught, which is square root of x minus x naught squared, y minus y naught squared. So this is just due to this one panel at a particular point called x comma y. So if you want to get all the panels to participate, all you have to do is integrate this, panel 1 plus panel 2 plus panel 3 all the way around. Then you get the stream function at x comma y from all this vorticity that we have placed all over the aerofoil surface. So the stream function at a point x comma y is the integration over all the panels. This is a closed integral because our body is closed. It doesn't have to be, but we just acknowledge the fact we are dealing with a closed aerofoil section. So adding the free stream velocity stream function plus the stream function produced or induced or caused by all these panels, we get a total stream function value. As we talked about earlier, no matter where you are on the aerofoil, the body itself is a streamline. It's a stream function of value c, so this is the constant. So this is the equation that we had to solve. This is an integral equation. The unknown is buried inside the integral. There's also an unknown here. This is called the integral equation of the first kind, Fredholm integral equation of the first side. So we get discouraged. Our unknown is buried in here. So we ask, why do we want to solve for gamma naught? What does it represent? What is the purpose? So this is the aerofoil panel, solid surface. So the fluid is at rest. Outside the velocity is going from left to right. These distances are very, very small. We are going to shrink to 0 because we are approximating the boundary layer by an infinitesimally thin vortex sheet. So now if you do a circulation around this contour, you always do counterclockwise. So 0 times delta S, that's 0, plus 0 times normal velocity. Why is 0? Because normal velocity is 0 and this height is also 0. Plus minus of v, because the velocity is coming left to right, not right to left. Minus of v times delta S naught plus 0, that's the circulation. So the circulation gets contribution only from this side. It's minus of v naught times delta S. So the circulation inside the contour gamma naught ds is minus of v times ds. So the tangential velocity is negative of gamma naught. So if we solve this equation, once you know the gamma naught, we know the tangential velocity. There's no normal velocity at the surface because fluid cannot penetrate the aerofoil surface. So this is the only velocity we have. So when we stick this into the Bernoulli equation, we get a pressure. So once we know the pressure, we could integrate it and get the lift. So this is how panel methods work in general. So Bernoulli equation says, as soon as you give me this velocity, which is this gamma naught, I can solve for the pressure. Velocity squared, if you give me, which is gamma naught squared, I can solve for P in dimensional form, or I can solve for the pressure coefficient in non-dimensional form. So aerofoil codes such as Xfoil and my own MATLAB based code, they compute the CP all over the surface at the center of each of the panels. You could also do viscous flow, which is a Navier-Stokes solver, ANSYS Fluent, Star CCM, OpenFOAM, software like this, they will compute these. Wind tunnel folks will measure the pressure over atmospheric pressure, which is the gauge pressure, divided by the dynamic pressure. They will compute these. So it doesn't matter how you compute the CP. Once you have the CP, you could integrate it to get the lift and the drag like we talked about in our previous modules. Now with the trailing edge, pressure must be equal. That means the velocity squared must be equal, because Bernoulli equation says P over rho plus 1/2 of velocity squared is a constant. So if the pressure is equal, 1/2 V squared above and below must be constant. That means the gamma squared upper must be gamma squared lower. This is spinning positive clockwise, negative. This is spinning clockwise, counterclockwise, positive. So they should be equal in magnitude, opposite in sign. Negative value, positive value, put the minus sign. So this is called the Coulomb condition. So we use this equation plus the Coulomb condition to solve for our unknown gamma naught and also our constant C. So we divide the aerofoil into a number of panels shown here. Each panel we integrate it. So if there are n panels, we assume that the gamma naught is a constant over the panel, piecewise constant. So instead of keeping it inside the integral, we bring it outside. So 1 over 2 pi is already outside. The minus sign is outside. This is the free stream velocity. Notice that we have introduced a subscript called I. This is the panel where we are computing the stream function. So this is the J is the integration over different panels. It may sound confusing. So aerofoil is made of J panels. They are located, their centers is at xj, yj. So you compute all the induced velocity due to all such J panels from 1 to n at this fixed point I, at the center of a panel called I. So this is the stream function that must equal constant. Now if you notice this is purely a geometric function. So if we could somehow analytically integrate it, then we are in good shape. So this represents the influence of a panel number J at a control point or the center of a panel called I. So we could call it A, which is a constant, subscript I, comma J. I is where we are computing the stream function. J refers to the panel where we are doing such calculations. So doing it that way, we get this system. This is Aij is the influence of the panel number J on index number I. So putting this in here, we get a nice system. If you have n panels, we get a n by n equation system. But we have a n unknowns for the gammas plus 1, n plus 1 unknowns. So what do? We add the Coulomb condition. So now we have n plus 1 equations, n plus 1 unknown. So this system can be very easily inverted. One could solve for the gamma, then gamma naught is found. So once gamma naught is known, we can find the pressure. Then from the pressure, we can find the pressure coefficient. We can integrate it to get the lift coefficient. So in my website, I have a panel method. You could just click on it. It's written in MATLAB. I have also included those things in our ebook, the complete listing, sample input, sample output, so that you could see how these things work. Industries normally use a more robust program such as Xfoil, because my program can only compute the lift. It does not compute the drag. How do you compute the drag? We have to introduce the boundary layer. So that's a topic for our follow-on lectures. There are other programs besides Xfoil. There's a program called Pablo that you could use it. We don't use a Pablo anymore. Most people use Xfoil. So we will show in some of our lectures how to use Xfoil to compute the lift coefficient and also the drag coefficient.